Warning: phthalic anhydride is irritating. Wear gloves and a mask when handling it. Hi guys, here is MIH. Phthalic anhydride is an especially versatile reagent in organic synthesis. Its most well-known use in aperture chemistry is as a precursor to lumino, but the nitration step is notorious for having a low yield, so I won't attempt it this way. Instead, I plan to convert the phthalic anhydride to phthalimide and perform a Gabriel amine synthesis with it. To start, I weigh out 27.5 grams of potassium hydrogen phthalate as our starting material. There are many people on YouTube who extract phthalate esters from gloves and electric cables, but phthalate-based plasticizers are getting phased out due to safety concerns, so it's difficult to find a product that contains a decent amount. Anyways, I dissolved the potassium hydrogen phthalate in around 100 ml of boiling water. To the clear solution, I then poured in a random amount of 25% hydrochloric acid. At first, nothing significant happens, but suddenly a large amount of white precipitate appears, which is phthalic acid. I stopped adding the acid when the pH reaches 2 and decanted the supernatant off to another beaker. As the mixture cools, beautiful crystals of phthalic acid started appearing. Those crystals reflect the light pretty well, so they can be used to make a cool ornament called the crystal rain bottle. After everything cooled down, I filtered the mixture and transferred the wet phthalic acid to a large beaker. I also placed a small beaker in the middle of the phthalic acid pile, and you'll see why in a moment. The large beaker was placed on the hot plate and heated to 300 degrees Celsius. At first, the water in the phthalic acid boils off. I didn't expect it to take this long, but I have to wait 30 minutes before all the water is gone. Apparently, phthalic acid traps a lot of water in its crystal structure. Now the water is basically gone, and the vapor coming out of the beaker became quite irritant. The phthalic acid starts to dehydrate and form phthalic anhydride, which sublimes and releases out of the beaker along with the remaining water vapor. I placed a flask of cold water above the large beaker to allow the phthalic anhydride to cool down and deposit. Soon, the phthalic acid starts to melt slowly. It actually decomposes around its melting point, but we still need to melt it completely. Meanwhile, some crystals are already depositing on the upper parts of the beaker. Their fluffy appearance proves that they are phthalic anhydride crystals. After a decent amount of crystals deposited, I removed the beaker off the hot plate and allowed it to cool. I then scraped off the crystals with a spatula. I found the small beaker useful as it can support the crystals from falling down into the phthalic acid melt. The beaker is then placed on the hot plate again, and the process repeated several times until little phthalic anhydride comes out. The annoying part of this procedure is that it is a batch process, and the beaker needs a long time to completely cool down. I'm sure there must be flow process optimizations that make this method much more efficient. After about 10 cycles, the phthalic acid melt stops producing any more phthalic anhydride, and I scraped any remaining crystals off. The final yield of phthalic anhydride is 14 grams, representing a 71.7% yield, which is quite good for this reaction. Thank you for watching, and see you soon.